Hello everyone. In this lecture, let us see the time domain analysis of first order RC circuit, that how an RC circuit responds when it changes from one steady state to some other steady state with respect to time, right? So I have taken a simple RC circuit where RC in series, right, with the energy supply source V volts. Right, initially I have taken the switch as open switch, right, the switch is open. Now at time t is equals to 0, I am closing this switch, right, I am closing this switch at time t is equals to 0. That means initially there was no current flowing through this, that means there was no potential difference applying across this capacitor. But when I close this switch, there is some amount of current flowing through this RC circuit due to the existence of potential difference between the terminals, right? So now writing the equation for the circuit, we get the supply source V is equals to IR plus, let me take the voltage across this capacitor as VC, right? Plus VC. Why? Because VC is nothing but C dV by dt. So with respect to time, the voltage across the capacitor changes. I want to study this circuit with respect to time, so that I have taken the voltage across the capacitor circuit as VC, right? Now V is equals to I is nothing but as I have told you, I is nothing but current flowing through the capacitor circuit, that is I, which is also flowing through the capacitor, that is I can write it as C dVc by dt or not, right? Plus VC, then bringing this VC to this side, I'll get V minus VC is equals to C dV by dt, right? Sorry, there is R also, R, right? RC dVc by dt, fine. Now rearranging this one, I'll be getting dVc by dt or dVc by V minus VC, I am bringing this V minus VC this side, is equals to minus 1 by RC dt, right? So from this I will be getting, integrating on both sides, what will be getting? Log of V minus VC equal to minus integral of minus 1 by RC is what? Minus T by RC plus some constant K, right? Now for finding out the value of K, go for initial conditions. So initial conditions. So what are the initial conditions here? Time t is equals to 0, the voltage across the capacitor was 0, alright. So substituting these initial conditions in this equation 1, substitute t is equals to 0, Vc is equals to 0 in equation 1, what will be getting? We will be getting, see, log V minus Vc, right, is equals to, this is 0, is equals to t is 0 and Vc is also 0, right? Vc is 0 plus K, that is K is equals to log V I am getting, right? So now taking this, substitute K in equation 1, I will be getting the total equation, that is log V minus Vc is equals to minus T by RC plus log V, right? So bringing this one to this side, I will be getting log V minus Vc by V is equals to minus T by RC, right? I can write this one as V minus Vc by V is equals to e power minus T by RC, where V minus Vc is equals to V into e power minus T by RC, taking V common from both sides, I'll be getting Vc is equals to V into 1 minus e power minus t by Rc. Same as in the last derivation, this is all nothing but mathematics, right? So I have got the equation for voltage across the capacitor as V into 1 minus e power minus t by Rc. Now I am taking the value of Rc as time constant tau. So substituting this one, I will be getting Vc is equals to V into 1 minus e power minus t by 5. Now let us see the behavior or the change in response of this capacitor for different values of t. So however at t is equals to 0, we have found out Vc is equals to 0, right? So now at t is equals to Rc or tau, we shall see Vc is nothing but V into 1 minus e power minus tau by tau, right? So that is Vc is equals to V into 1 minus e power minus 1. Now substituting the value of E in the equation, we'll be getting Vc is equals to 0.632 volts. That is nothing but 63.2% of the total maximum voltage, right? So that means for different values of t, if we now draw the response of this capacitor voltage, see this is t, V, right? So at t is equals to 0, Vc was 0, that means here. Now at t is equals to Rc or tau, its response is like, it is Vc is equals to 0.632, that means it is not maximum. It has still more some time to reach maximum, right? If you still go on increasing the value of time, then at some point of time which is greater than t is equals to Rc, the voltage across the capacitor goes to the maximum point, right? So this is the value corresponding to 63.2% of maximum voltage across the capacitor. So this is the response of the RC circuit for difference in time or for change in time. So during closing of switch means initially it was open stage to close stage. Open is one steady state, close in another steady state. From opening to closing, this is the behavior of the circuit, right? So now let us see what happens during discharging. Right? During discharging, what happens to the capacitor? Let us see now. So during discharging, that means initially the switch is closed. Now I am trying to open the switch. Right? That means at t is equals to 0. Right? The switch is closed. Closed means how much voltage is appearing across this capacitor? That is fully charged. That is the capacitor voltage is nothing but V. Maximum voltage from the supply is applied across the capacitor terminals, right? So now let me write the equation for that. Now initially it was closed. Now I am trying to open it, right? Open is my next steady state to be achieved. So the equation comes like Vc plus IR is equals to 0 during opening. Why? Because open, that means there is no voltage applied across this capacitor now after opening, right? This is for after opening, this is the initial condition. Be careful with the difference, right? Now again substituting the value of Vc here, we will be getting Vc equals to, I can write minus Rc dVc by dt or not, right? So this comes like dVc by Vc equals to minus 1 by Rc dt. Now integrating on both sides. I'll be getting integral of dVc by Vc is equals to integral of minus 1 by Rc dt, which gives me log Vc is equals to minus 1 by Rc or minus t by Rc plus k. Let me take it as equation number 2. Right? Now to find out k, put the initial conditions. put initial conditions. What are those initial conditions? This one. T is equals to 0 and Vc is equals to V. If you substitute this one, you will be getting our K is equals to log V or not. Because Vc is equals to V and T is equals to 0, so that K is equals to log V. Now put K in equation 2, right? You will be getting log Vc is equals to minus T by Rc plus log V. So rearranging this one, we will be getting log Vc by V is equals to minus T by Rc, implies I can write it as Vc by V is equals to e power minus T by Rc, where Vc is equals to V into e power minus T by Rc. So Rc I have taken as tau. Tau is equals to Rc, time constant, right? So now let us see the behavior of RC circuit for different stages of T at discharging time. Initial condition is this one. So let me see now what happens to the response at T is equals to tau, that is Vc is equals to V into e power minus tau by tau. That gives you V is equals to e power minus 1. When we substitute the value of E, you will be getting Vc is equals to 0.368 volts. That is at time constant, at value of time which is equals to Rc, values of multiplied values of resistance and capacitance, the capacitor is still not completely discharged. That means to obtain complete discharging of the capacitor, you have to still increase the value of Rc which is greater than tau, right? Now let us draw the response. So if you draw the response, you will be getting like this, V. So initially at T is equals to 0, what happened? It was maximum, right? Maximum, I am taking it here. Now at T is equals to tau, it was 0.368. That means it is reduced, right? The value is reduced, value of V is reduced. Now if you still go on increasing the value of time, at a particular stage it reaches to 0, right? So this is the response of the RC circuit, where at T is equals to tau, it is 0.368 volts. This is the response corresponding to Vc, that is V into e power minus T by Rc, right? So this is about charging and discharging of the capacitor in an RC circuit. So hope you have understood what is time domain analysis of RC and RL circuits with respect to time. Thank you.